In section 14.4, we're going to discuss linear correlation. This will be the last of our chapter 14 sections on linear regression and correlation. Again, I'd like to start with posing a question here, and of course the answer is going to be directly below it. The question might come up is the following. Let's say we have fit a linear regression line through data points. Okay, and we may be interested in knowing, well, how strong of a linear relationship is there between the two variables, the predictor and the predicted variables? That would be the x and y. Now the keyword here, I have it highlighted. In fact, the keyword here is linear. Okay, so that's what we are primarily interested in this section. Now, as far as our measure of linear correlation, we're going to use Pearson product moment correlation coefficient. Now, most textbooks simply call this a correlation coefficient. They leave the three words Pearson product moment out of it, but that's what it is. Whose founder, Professor Carl Pearson. It's named after him. Okay, so here's a formula actually that you will see. I have here the formula for you, but we're not going to use this formula. We're going to actually use the StatCrunch, and in fact I don't have a StatCrunch run for you in this one. If you recall, we've in the last two sections 14.2, 14.3, we did an exercise in StatCrunch, and in that output we had r squared, and directly above r squared there is r. So that's, you can refer to those outputs for a numerical example. I just want to go over the discussion of what does this correlation coefficient do for us. So I'm interested more in the significance of it rather than its computation, because again, it comes out on the regression output. And it's usually directly again below the equation of the regression and directly above the r squared, which is coefficient of determination. So I'm going to skip over these formulas, although they're there, but just want to start with a note here. Okay, now there is very close tie between the coefficient of determination that we discussed in section 14.3 and the linear correlation coefficient r. And here's how the two are related. R is equal to square root of r squared. And of course we have plus or minus because of the square root principle. Now, because r squared lies between 0 and 1, so its the square root actually lies between -1 and 1. Okay, so that means the Pearson product moment correlation coefficient can be no less than -1 and no higher than 1. So it ranges between those two numbers. And also here, as far as since we have plus or minus, right, in our formula here, so how do we know when to use plus and when do we choose minus when we take the square root of r squared? Well, the sign of r is always consistent with the sign of a slope of the regression line. So if the slope is positive, I have it down here. So if the slope of the regression line on the output, you read it and it's positive, then correlation coefficient will be positive. If the slope of the regression line is negative, then so is the correlation coefficient. And here I have three notes coming up. The first note is that when we calculate or compute R measures the degree of linear association between two variables. Again, the emphasis is on the word linear here. Everything in this section has to do with linear. Okay. And because it measures the linear association between x and y, then it can only be used in the case of a linear regression, not in the case of a nonlinear regression. Okay, we don't do any nonlinear in this course. And finally, my third note in this segment is that we have actually two types of correlation. Okay, now this is not in your book, but I'm just going to mention it anyhow. So we have what we call observational correlation, and then we have experimental correlation. Okay, now as the word implies, with observational, you simply observe the relationship between X and Y. So for example, I'm going to look at I have a couple of examples, in fact, at the very end of this lecture of observational correlations. So for instance, I may be looking at the variation between the chicken consumption and age. Well, I don't think age determines, how much exactly a person consumes chicken, but there may be a high correlation between that. Or I can, for instance, look at a person's income and compare it to home prices in a region. Okay. In fact, a good example of observational correlation would be the instance where it has been shown that the sales of chewing gum correlate very highly with the crime rate. So in other words, as the sales of chewing gums increases, so does the crime rate. But again, these are merely observational correlation. We cannot draw causation. We cannot say that the reason for the rise in crime is because of the increased sales in gums. Okay, so just want to clarify that one. So we cannot draw causation in the case of observational correlations. However, if the correlation is experimental, then we can draw causation. So an example of that, for instance, might be if I'm looking at the relationship, the correlation between temperature and moisture content of, let's say, a cake. Okay, at a fixed temperature, for example, let's say, I'm sorry, not a fixed temperature, but for a fixed period of time. So for example, let's say I'm baking 4 cakes, all for about 20 minutes. Okay, one cake, I'm baking it at 375 degrees Fahrenheit, the other one at 400, 425, 450. Okay, so I have these 4 cakes that I'm baking each for 20 minutes. So I'm controlling for time, and I'm looking at the effect of temperature, and then somehow I can measure the moisture content of the cake. So there's going to be some kind of an association. It may be linear association between moisture content and temperature in this case. And if that correlation is high, then I can draw causation, because it's in an experimental situation. I can say that the temperature is what's causing the moisture content. Remember, I kept the times the same for all 4 cakes, 20 minutes each. So that's the idea of being able to draw causation in the case of experimental correlation. So here I have a couple of examples in trying to find R given R squared. So let's say R squared is 0.8, and you're also given the knowledge of the slope of the regression line, that the slope is 31.67, and we want to find R. So we're going to take the square root of R squared, right? And it's going to be square root of 0.8. That makes it 0.8944. Now, because the slope's positive, so is R. And we can interpret this as a strong positive correlation between X and Y. I will show you the yardstick that we use, the guide, if you will, on what makes it a strong or not so strong. Okay, the number itself. Here's another example. Let's say this time I'm given R squared is 0.4, and the slope of the regression line, I made it negative, just made up numbers. And again, we want to find R. So R is found by taking the square root. But notice this time, because the slope of the regression is negative here, then this will be negative also. So these two will always match. Okay, there's got to be the same. And so hopefully that will clarify what we stated earlier. And that correlation of 0.63 seems to be a moderate reciprocal correlation. That's what negative correlations are. Negative correlations are referred to as reciprocal, or some call it inverse correlation. Okay, inverse, reciprocal, or simply negative correlation. That means as the value of one variable increases, the other one decreases. That's the reciprocal relationship of the two. Okay, now let's continue on. And here's a guy that I was mentioning about. And there you go. So I have a number line here. The center is at 0. Again, I can draw these and then erase them later. So here you go. That's the center of that number line. And this is where the center is, right in here. That's my 0 line. Okay, now, if R turns out to be 0, then therefore there is no linear correlation. Okay, again, the emphasis is on the word linear here. There is no linear correlation between X and Y. And then look, as we go from left to right, the numbers are increasing. Okay, so I'm actually having a number that is 0.4, that is 0.6, 0.8, and 1. And look at the strength of linear association as we go in that direction. It's getting stronger. We go from poor to weak to moderate to strong. At R equal 1, when R is exactly 1, that's the case where we have perfect positive linear correlation between X and Y. Okay, what does perfect positive looks like? We'll see this in a moment. The author actually has several charts that we're going to utilize. And the other end of a spectrum is right in here on the negative side. Notice the interpretations are kind of the same as far as what is strong and what is not strong. So R equal 1, strong, positive. R equal negative 1 would be strong, but this time actually at R equal 1 we have perfect positive. The other end of scale we have perfect negative correlation. Okay, so just want to point these out. These are symmetric with respect to the center. And then of course you have your varied degrees of correlation. As you go down the number line from 0, work your way toward negative 1, the correlation is actually becoming stronger. It goes from poor to weak to moderate to strong. Okay, the only difference again between positive and negative is the direction of correlation. Now, here are some examples of correlation. So if you look at, I'm actually looking at this one now. Okay, if I look at this one, this is a case where you have perfect fit. You see how these data points all lie on the same line? So there is actually no error associated with these data points. So all the points fit perfectly on the line, or the line goes through every single point. There is no error. There is no residual in this case. So here's again the case where R is 1. You have perfect positive correlation. Look at R equal negative 1. It's kind of the same idea. Every point falls directly on that line. So again, there is no residual, no error. There is no miss. So you have perfect fit. Negative versus positive. And then after that, like for instance in this one where R is 0.9, so we begin to see these points kind of scatter. Okay, they sort of fall apart. So look at the scatteredness of this data versus this other data to its right. You see how they're kind of falling apart, and as they do, look at the correlation. There's still that slant, positive slant, or inclination of the line, but the absolute number for correlation is actually dropping as these points begin to disperse or fall apart. And then we have it on the negative side of things, the correlation negative. Look at this, negative 0.9 versus positive 0.9. They're kind of mirror image, and you kind of see how they behave. The data is behaving. So, and what happens at r near 1, this is r almost 0, in that there's no linear correlation between these two variables, between x and y. And if I was to fit a straight line through these data points, the straight line would be right there, and it's going to end up being at y bar. Means your best prediction of y values is just choose the average y values. That's the best you can do in this model, because there's no pattern, there's no trend, there's no trend whatsoever in this data. Okay, and there you have again the case of r equals 0. Now let's keep going here. This one is, I just want to clarify the relationship between r and r squared again. Even though we take the square root of r squared and it becomes r, so mathematically they're related to one another. If you square your correlation coefficient, it becomes r squared. Okay, but other than being related in the way of the mathematical formula, the interpretation is actually totally and completely different interpretations. Okay, so I have a couple of bullets about this. So first of all, r squared is a percent. Okay, r squared is a percent. That's what that is. Whereas r is not a percent. It's a decimal, it's an index, and in fact, there are no units associated with r. It's an index, means it is unitless. There is no unit attached to it. Okay, and r squared also, there are no units attached to r squared either. But the key difference between them, other than fundamentally they have total different interpretation, is that even as numbers, r squared is a percent, whereas r is not a percent. It's simply a decimal. Okay, and r is only used as a measure of linear association. We try to gauge the strength of the association, and that is a linear association. That's what r is intended. So in the case of nonlinear and multiple regression, we don't even use r. Okay, now r squared by contrast is used in all regression modeling. Okay, even in simple linear, where we use r as kind of a complementary measure of association, r squared and r there kind of signal the same ideas. R squared tells us that your model is either adequate, strong, or weak, and the association between x and y as it is depicted by r points to that same direction if the model is a linear model, simple linear regression model. And I have an example actually that I will clarify this for you through an example I made up. So we're getting close to actually the example I mentioned. Now in here what I have is I've just made up this data. Okay, so we have clearly a data that exhibits some kind of a bending. So here the data points, whatever they are, these data points actually don't have a secular trend. Okay, they do not. In other words, they don't follow a line like this. See that? They don't fit on that line. So they don't exhibit any kind of a secular trend. However, here r squared will be high provided if the model is nonlinear, right? Clearly anything that's not a line, we call it nonlinear. And you can see again, you see how that there's a nice bend to this data, and the more I boldface it, you kind of recognize the shape of this curve. That looks like a parabola, doesn't it? So if I if I knew how to fit a parabola through this data, perhaps I can pick up a high R squared value, and then I'll be able to make my predictions, right? Well, I've actually done that in StatCrunch. Now, here is a more specific data set. I actually created this data. So I know what the mathematical expression is for it. I'll give you the expression in the end that I just made up, and it's very simple to do. But anyway, I created the data that follows a parabolic model. So what do I mean by that is this. There you go. See how a parabola fits perfectly? Well, not perfect, but very closely it resembles the pattern that's in the data. Now look at if I draw a line here, folks. What do you think? Which one is a better model? These points are very close, right? Very close to the red curve. Whereas, look at if I use, what do you call it? Let me remove this one, keep the blue. And if I use the straight line I have here, the predicted value for this observation will be here. Predicted value for that will be here. See how far off they are? Look at those. Way off. True? And that's the drawback of this linear fit. You see that? So there's a lot of residual or error associated with this kind of a model if it's a linear model. Okay. Now, what I've done actually, I've done that. There you go. I fit a line through these data points. Okay. And here I have a fitted line. Okay. Now, for this fitted line that I fit through the data points, look at the correlation coefficient here, folks. Look at that correlation coefficient, -0.2. That's very poor, isn't it? And look at R squared. It's almost 0, isn't it? It's near 0, means very, very poor model for prediction. So we're not going to use this straight line. So here's where R is going to be poor, and R squared confirms. Both of these numbers tell me the same thing. Okay, both of them are telling me that this linear fit is a poor fit. Now, let's say we know how to fit a parabola through these data points. And check this out. Here I fitted the curve through these data points, and look at that curve. Isn't that nice? In a couple of instances, it actually goes through almost this one, this one, this one, this one are almost on the line, and this is actually not too far away from the predicted value, which is that. Look at the predicted values. These three, the distances, the vertical distances aren't too far away from it, right? So this is actually a pretty darn good model. Okay, a parabolic model. And check this out. Look at that R squared. And this is what we're talking about. And you can actually still see the R squared that's up here. This one. See how lousy it was for the line? And look at this one. What a difference, huh? And that's what we're talking about. So R squared is always used as a way to check the adequacy or the fit of the model. But we don't use R in this case. For this one, we do not use R. It would not make sense. Do not use R here. Because on one hand, we're saying the parabola, the nonlinear model, fits almost perfectly. And then on one hand, if we do R, we're looking at the strength of linear association. So it doesn't make sense. So what I mean here is that do not do this. Let me put these X's here. Do not do square root of 0.9719 and they'd say R is that for this model. It just doesn't make sense. We cannot do that. Okay. Only for linear straight line we can do R. That is, take the square root of R squared. Otherwise we don't do that. Do not use R here. Okay. Now, and just to show you again, because I made this up myself, I know the actual mathematical model. This is what I actually did. I said, I was fooling around with this. I said, let me think about a quadratic equation. Sorry about this. And let me make up an example to where you can see a nonlinear fit through the data. Okay, now we're going to end this video and this lecture by looking at some spurious correlations. Now remember, these are fake correlations, and I have a couple of them. Both of these are actually observational, and I think you'll enjoy this. This is actually off of a internet. I grabbed it from the internet, but the data source is actually valid. See, the data source is one is the Department of Agriculture and Center for Disease Control, CDC, which you hear a lot about it nowadays. There you go. Okay, so two reliable source of information. And check this out. This is actually looking at, let me get rid of these. Okay, so what are we looking at here in these models? Well, we're looking at per capita cheese consumption and its correlation with number of people who died by becoming tangled in their bed sheets. Quite interesting, right? So the correlation between these two variables, check this out. Look how high the correlation that is, almost 0.95. Now I see one flaw. Everything looks perfect in here, but the person who's put this together, there's one flaw in this presentation, and that is right in here. Remember, correlation is not a percent, so that is inaccurate. Okay, they should not be using percent symbol there, but just to point that out. But nonetheless, the correlation, linear correlation, is pretty high. But again, we're not drawing causation. We're not going to say that per capita cheese consumption goes high or increases because as a result of number of people who die by becoming tangled in their bed sheets, and vice versa. Here's the other one. Check this one out. This one is looking at the correlation between the age of Miss America. Okay, the age is over here. It's almost 19 to about 25 years old. Okay. And murders by steam, hot vapors, and hot objects. The correlation is 87.87, not 87%, but simply 0.87. Okay. So it's going towards a strong correlation, positive correlation between them again. Okay, so again, just want to show some of these correlations to you and kind of make a conclusion here, just to be careful that both of these examples are examples of observational correlation. So as such, again, we cannot draw causation. So there's no causation in this case, and it cannot be implied or drawn as a result. Okay. So with that, we are done with this lecture, and hopefully you followed everything we did. And if not, please review the lecture, and hopefully it makes sense the second time, makes more sense. But with that, we are done with this lecture.